The engineering term is brittle fracture, and it happens when steel loses its ductility in cold temperatures and under stress. The steel the Liberty ships were made from was fine in normal conditions. But in the North Atlantic in winter, with the hull under load from cargo and wave action, the steel became brittle. A small stress point, maybe a sharp corner in the design, maybe a flaw in a weld, would suddenly crack. And that crack would race through the hull like lightning. Image 2 prompt, close-up technical illustration of welded ship hull showing crack propagating through continuous weld seam, arrows indicating crack direction and speed, cross-section view showing brittle fracture. Cold steel, technical diagram aesthetic with dramatic lighting. By 1943, the situation was critical. At least 3 Liberty ships had broken completely in half. Dozens more had serious cracks. Ships were literally falling apart at sea and in harbors. The Navy convened emergency investigations. Metallurgists were brought in. Engineers examined every aspect of the design and construction. And they found multiple contributing factors. The steel chemistry wasn't ideal for cold weather, there were sharp corner designs that created stress concentration points, welding quality varied wildly between different shipyards, and welders were being rushed to meet production quotas. But here's the challenge: they couldn't stop building Liberty ships. The war depended on them. They couldn't redesign the entire class because hundreds were already built and hundreds more were under construction. They needed a solution that could be applied quickly to existing ships and incorporated into new construction without slowing down production. The engineers proposed various sophisticated solutions, different steel alloys, modified hull designs, improved welding procedures. All of these would help, but they would take time to implement. Then a welder came forward with what seemed like the simplest, almost stupid idea. He said, "What if we just drill a hole at the end of the crack?" The engineers looked at him like he was crazy. "You want to deliberately put a hole in the hull? That makes no sense." But the welder explained his reasoning. A crack propagates because of stress concentration at the sharp tip of the crack. That sharp point focuses all the stress into a tiny area. But if you drill a hole at the end of the crack, you eliminate the sharp point. You distribute the stress around a circular opening instead of concentrating it at a sharp crack tip. The crack stops because it has nowhere to go. The engineers were skeptical. But they were also desperate. They tried it on the SS Benjamin Huntington, which had developed serious cracks. They drilled holes at the ends of each crack. The cracks stopped growing. They monitored the ship carefully. The holes held. The ship made multiple voyages across the Atlantic without the cracks extending. It worked. This became known as a crack arrestor hole or a stop drill hole, and it was immediately incorporated into emergency repair procedures for damaged Liberty ships. But the genius went further. Engineers realized they could use the same principle proactively. They identified the high-stress points in the Liberty ship design, particularly around the corners of hatches and at the connections between deck houses and the hull, and they added what they called crack arrestor straps or doublers. These were reinforcing plates with rounded edges riveted or welded over the high-stress areas. The combination of the drilled holes and the crack arrestor plates transformed the Liberty ship program. Ships that would have been scrapped were returned to service. New construction incorporated the modifications from the start. The catastrophic failure rate dropped dramatically. But they didn't stop there.